You know, every single night, we all do something that's kind of like a magic trick. We lie down, we close our eyes, and for about 8 hours, poof, our conscious self just vanishes. And then it reappears in the morning, sometimes with the leftover weirdness of a dream. So what is actually going on inside our heads during this nightly disappearing act? Let's get into it.
Here's the thing. We have these incredibly detailed maps of the brain's physical structure. We know the parts, we know the connections, but they still don't answer the biggest question of all. Why does all that electricity and all those chemicals feel like anything, you know? We know all the parts of the engine, but we still don't really get how it creates the actual experience of driving.
So to get closer to an answer, science is basically coming at this problem from two very different but equally important angles. One way is to look at all the individual parts, and the other is to look at the overall patterns that those parts create together.
Let's stick with that car analogy. Think of it like this. One view is all about studying the engine, right? The pistons, the fuel lines, all the physical machinery. The other view doesn't really care about the pistons. It studies the car's speed, its acceleration, its path down the road, the motion itself. They're both describing the same car, just at totally different levels. Okay, so the first view, that's what we call the mechanisms view. This comes from clinical neuroscience, and it's all about what we can physically see and measure. We're talking specific brain regions like the brainstem and the thalamus, which is like a big sensory switchboard, and the flow of neurochemicals, the electrical signals you see on an EEG. Basically, it's all about the brain's physical hardware.
And then you have the dynamics view. This perspective is way less concerned with any single component and much more interested in the flow, the patterns, and the relationships between all those parts over time. It's really trying to describe the brain's software, how all that machinery works together to produce a structured experience, like a thought or a dream or a feeling.
Okay, so you've got these two different views. How do they actually clash? Well, let's start with the most basic question. When you're in a deep, dreamless sleep, is your consciousness completely turned off, or is it just something else?
From the mechanisms-based perspective, the answer is pretty simple. Key parts of the brain that handle awareness, like that thalamus we mentioned, are basically shut down. So if there's no measurable activity there, and, this is crucial, you can't report having any experience, then consciousness is just gone. It's an on-off switch, and it's in the off position. End of story.
But the dynamics view comes back with a really interesting counterargument. It says, whoa, hold on a second. Just because that big, global, reportable awareness is gone doesn't mean all processing has stopped. From this angle, consciousness isn't a hard switch at all. It's more of a gradient, a matter of how connected different parts of the brain are at any given moment.
To put it really simply, one side sees a light switch. It's either on or it's off. The other side sees a dimmer switch. The light might be turned down so low that you can't even see it, but the circuit is still active. It's just operating in a different, much less connected state.
This whole debate leads us straight to the next big disagreement, the absolutely bizarre world of our dreams. Are they just random brain static, a sign that something's not working right? Or is there actually a hidden purpose to all that madness?
So the mechanisms view points out that during REM sleep, our prefrontal cortex, that's the part that handles logic, reason, and telling what's real, is pretty much offline. And because of that, dreams look a whole lot like waking hallucinations or even psychosis. So from this point of view, dreaming is basically a kind of temporary, totally normal dysfunction.
But the dynamics view offers this fascinating reframe. It says, yeah, it looks like chaos, but it's controlled chaos. It's not a bug, it's a feature. The idea is that the brain intentionally loosens up its logical rules so it can do a safe offline reorganization of emotional stress and memories.
So here's how that's supposed to work. First, the brain's logic centers kind of relax their grip. Second, this lets all these emotional pressures and unresolved feelings just flow and redistribute themselves in a safe internal playground. And finally, that whole process helps us reorganize and integrate our memories, all without the risk of you actually acting out those bizarre dream scenarios in your bedroom.
And all of this leads to an even deeper puzzle. After a night of being off, or having these wild, fragmented dreams, how do you wake up still feeling like you? Where does that stable, persistent sense of I come from?
The mechanisms view, true to form, has a pretty clear answer. It points to a specific set of brain regions called the default mode network. This is the network that lights up when you're just daydreaming or thinking about yourself. So the idea is simple. When this network is on, you have a sense of self. It's the hardware that creates the I.
But the dynamics view argues that's only half the story. Sure, that network might represent the self in any given moment, but that doesn't explain why it's so stable over time. Instead, it suggests our identity is what's called a stable attractor, a kind of default pattern that the brain's complex activity just naturally settles back into, night after night.
So what on earth is an attractor? It sounds complicated, but the idea is actually super intuitive. Just imagine a marble in a bowl. No matter where you push it along the side, it always rolls back to the very bottom. That point at the bottom is the attractor. The dynamics model is saying your self is like that. It's not a physical part, but it's the stable, default pattern your brain activity always returns to.
So, we have these two views that seem to be totally at odds with each other. One's all about the physical parts, the other is about the patterns. Does one of them have to be right and the other wrong? Or is there a way to bring them together? Well, as this whole debate has evolved, it's become pretty clear they aren't competing views at all. They're actually two sides of the same coin. One perspective is describing the brain's hardware, all the physical mechanisms, and the other is describing the software, the dynamic patterns that run on that hardware. You absolutely need both to understand the whole system.
And this really points to the future of neuroscience. It's not about proving that consciousness is just chemicals or that it's just patterns. The real progress, the real breakthroughs are going to happen when these two perspectives start working together.
So what does that collaboration actually look like? Well, it's a really cool feedback loop. The dynamics models can create new, testable predictions, ideas about how an experience should unfold or what a dream should feel like. And then clinical neuroscience can use its incredible tools like fMRI and EEG to go in and see if those predictions actually match what the brain's hardware is doing. And why does any of this matter? Because this synthesis, this teamwork, it marks a huge leap forward. It's the moment science moves beyond just making a long list of the brain's parts and starts to build a real explanation for the mind itself, for our subjective felt experience of what it's like to be alive.
And that leaves us with one last, kind of mind-bending thought. For centuries, scientific breakthroughs have always meant discovering a new particle, or a new planet, or a new piece of anatomy. But what if the key to understanding ourselves, what if the next great frontier isn't about finding a new piece of the machinery at all, but about finally decoding the patterns of its motion?